In atomic structure, probably the hardest calculations you have to do are the time of flight calculations for mass spectrometry. The main reason for that is just because it involves the trickiest rearranging. It involves a lot of numbers in standard form. And there's loads of places where you can just make silly little mistakes when typing it into your calculator, basically. Even if you know how to do these, because there's so much standard form and square rooting and fractions, typing it into your calculator, you have to be really careful. And that's where people mess these questions up, even if they know what they're doing. So there's only really 4 different questions they can ask. One about distance, one about working out time, one about working out mass, one about 2 different isotopes, and then having to use both of them. And if you can do those 4 types of questions, you should be able to tackle anything they give you. And I'm going to go through 4 of the questions from the tasks in the question pack, and that is because we're just looking here about how you do the questions. I'm not going over the actual past paper questions because you need to be able to develop the skill of looking at a past paper question, thinking, what does that question ask me? What is it looking for? And then once you've worked that out, you can link it back to one of these questions. Is it a past paper question where they're asking me to work out time, in which case you want to look at the task question that you did that was asking about time. The method's going to be the same. It'll just be different numbers in a different element. So we're going to start off with the ones that make you work out distance. So look at what information they've given you. They've given you a kinetic energy. They've given you a time. And that's it. To use either of these 2 equations, and they'll always give you the kinetic energy equation and speed equals distance over time, or a weird, horrible hybrid version of the 2, which I hate using and think it makes it so much harder when they give you that to rearrange. So I just tend to remember these. You need 2 bits of information. Now, the other bit of information we do actually have is the mass, because they've given us the mass number of potassium, 40. And because they've given us that mass number of the isotope, we can work out the mass in kilograms. That's where we're going to start off. So it's going to be the mass number. That tells us the mass of a mole. We want the mass of a single ion, so we have to divide it by Avogadro's number. Oh, hello. There we go. That gives us the mass of an ion isotope in grams. We want it in kilograms, so we have to divide it by 1,000, which is the same as timesing by 10 to the minus 3. That gives us 6.6423 times 10 to the minus 26. Now, when you've got the mass of a single ion, it's going to be a teeny tiny number because an ion is a tiny, tiny thing. So it should be times 10 to the minus 25 or times 10 to the minus 26. We're talking tiny. If you get times 10 to the minus 23, you probably haven't divided by 1,000. If you've got times 10 to the plus 23 or plus 26, you're probably times by Avogadro's number rather than divided by it. But that's your first, am I doing this right, logical check. So once we've got the mass, we can put it in the kinetic energy equation. So kinetic energy equals half mv squared. We want to work out v because that's the only unknown. So we're going to times both sides by 2 to get rid of the half. And then divide by mass. So v squared, we're just going to leave it as v squared for now, because as soon as you get more fractions involved, it's easier to mess things up. We've got 2 times 5.2 times 10 to the minus 16 from the question, divided by the mass, which you've just worked out. If you've messed up the mass calculation in the first step, you can always get an error carried forward mark here for rearranging that equation correctly and substituting in the numbers you think are right. So v squared equals 1.63 times 10 to the power 10. And then if we square root the answer, then v, just v by itself, is going to equal 127,748. Now, meters per second. One thing to notice is that in the question, all the bits of data they've given you are to three significant figures, although in this case that is also 2 decimal places. All my working out, I've done 2, 5, 6, 7 significant figures. The important thing is, when you work a number out in a calculation and then use it in the next step, never ever round to less significant figures than are in the question. If I rounded to 2 significant figures, I'd end up with the wrong answer. If I round everything to 3 significant figures, the same as in the question, that would be fine. In the actual answer and in the mark scheme, they'll give you a range of numbers which you can get, and that's based on rounding everything to the same number of significant figures in the question or with no rounding whatsoever. As long as you're somewhere in there, you will be okay. I always tend to round just to 5 significant figures because then I don't waste too much time writing numbers down, but also feel I'm maintaining some degree of accuracy. So now we've worked out velocity, which is up here. We can now put it into the speed equals distance over time equation. We'll just rearrange that. So distance equals velocity times time. So our velocity we've just worked out. And I'm just going to write it out again here. Times it by the time, 1.54 times 10 to the minus 5. Now, the reason I've written it out again is because if I've messed up this stage, maybe I've forgotten to square root it, or I've put the numbers into my calculator wrong and I've only square rooted the 1.63196 rather than the whole bit times 10 to the power minus 10. I've made some kind of mistake. I've written it out again. I've shown that I've made a mistake, but I've used that wrong number in the next step. I'd still get an error carried forward mark because I'm not being penalised for that same mistake I made early on in the calculation. I'm only going to get penalised for that mistake once. If the rest of my calculation is correct but using that wrong number, I'll still be credited for that because you know what you're doing. And then your distance comes out as 1.97 meters. Now this time, because that's my final answer, I'm going to give it to the same number of significant figures as the question. The numbers in the question were 3 significant figures. My final answer will be 3 significant figures. And if you're wondering where the marks come from, first mark for calculating the mass, second mark for rearranging the kinetic energy equation and substituting the numbers, third mark for square rooting it, fourth mark using speed equals distance over time and giving your answer to 3 significant figures. So the next thing they could ask you is to work out time. And actually, this is virtually the same as the last one. The only difference is going to be that final step with how we rearrange speed equals distance over time. So first step, work out mass in kilograms. This time we're playing with some manganese, always exciting. If you look at how that grows naturally, it looks like someone's just drawn random pencil lines on a rock. It's an absolutely gorgeous mineral. Almost looks like a plant. It's very weird. So that's our mass. We then want to put it into the kinetic energy equation to work out velocity. But again, we're going to work out v squared rather than v, because that means there's one less step in this calculation, so we're less likely to make a mistake in the calculation when we're typing into the calculator. You'll be surprised the amount of people that refuse to slow down their calculations because they think it's wasting time in the exam, but all they do is end up typing stuff into the calculator wrong and losing marks because of that. Nobody thinks they're that person, but generally the people who really don't think they're that person are that person that makes that mistake every time. So we've worked out v squared, square root it to work out v, which is always tends to be about 100,000, or at least in that order of magnitude. So that's our velocity. Then we want to rearrange speed equals distance over time. So time equals distance over velocity. I probably should stop mixing up speed and velocity, but for all intents and purposes, in this situation, they're the same thing. and you end up with 1.37 times 10 to the minus 5. You've got to think, ooh, not minus 15, just minus 5. So you have got a single ion. It's going to have a tiny, tiny mass. It's only traveling somewhere between 1 and 2 meters, so it's not traveling a long distance, and you're traveling at 100,000 meters per second. Therefore, the actual time it takes is going to be a tiny number as well. So the time is always times 10 to the minus 5 normally. So that's how you work out time. It's the same method as distance, just that final step with rearranging speed equals distance over time is different. Now this type of question confuses a lot of people because it starts off differently to everything you've done before. So if you think about our two equations, kinetic energy equals half mv squared, that's normally the one we use first. Now, do we have enough information for that? Do we have kinetic energy? Yes, we do. Do we have mass? No, because that's what we're trying to calculate. Have they given us velocity? No. So normally this is the first equation we use, but actually we can't do that this time. This time the first equation is going to have to be the velocity equation, and we're going to work out v. So velocity is distance over time. Our distance is 110 centimeters. We need it in meters. So first thing to do, convert that into meters. 1.1 meters, divide it by the time, and your velocity should come out as, again, in the range of 100,000 odd. I'm going to go to more decimal places or more significant figures than the question. Again, everything in the question is 3 significant figures. I'll go to, in this case, 8. So now I've got velocity. Now I can use the kinetic energy equation. And the only thing we don't know this time is mass. So we're going to have to rearrange it to work out mass. So we've got half mv squared. I'm going to times both sides by 2. So I've got 2 kinetic energies equals mv squared. I want I've got velocity on work out mass, so I'm going to divide both sides now by v squared. So mass equals 2 kinetic energies divided by v squared. Now you just substitute in the numbers from the question. So they've given you kinetic energy, divide it by velocity. Don't forget it's velocity squared. Be careful with how you type this one into your calculator. What you don't want it to do is the 2 times 3.81 times 10 to the minus 16 divided by the velocity and then square all your answer. You just want to square the velocity bit. And then your mass comes out as 4.6468 times 10 to the minus 26. Again, that makes sense. We're talking about the mass of a single ion. It's going to be tiny. And this is in kilograms, remember. Now, the question says, use this information to calculate the mass in grams of 1 mole of these silicon ions. We've got the mass of a single ion in kilograms. So we want to convert that into grams. So we have to times by 1,000. Anybody who uses a calculator for this, you're more likely to make a mistake when you're using the calculator. If you times by 1,000, the only thing that's going to change is the power of 10. So it's going to go just add 3 to minus 26. It's going to go to minus 23. That gives us the mass of a single ion in grams. So to work out the mass of a mole, or the mass of 1 mole, that's going to be the mass of 1 ion times Avogadro's number. Because there's Avogadro's number of ions in a mole of it, we've got the mass of 1 mole. We want to work out the mass of a mole of it, so times it by Avogadro's number. It really is worth getting straight in your head what a mole is and what Avogadro's number is. because then you don't have to remember equations, you can actually just logically work it out. So a single mole is going to weigh 27.98 grams. We'll have a mass of 27.98 grams. That's the first part. Then use your answer to state the mass number of this silicon ion. Any ion has to have a whole number, mass number. So 27.98 is pretty much 28. So the ion is going to be silicon 28. And again, if we think about where the marks come from here, working out the mass is going to be 1 mark. Working out rearranging this equation will be the second. Third mark. For working out the mass and substituting the numbers in. Fourth mark, doing that conversion, timesing it by Avogadro's number. Fifth mark, getting to that 28. So that's how you work out mass. Now, this question is probably the hardest type of question they can give you, but is always or normally worth the fewest marks as well. So they've given us 2 different isotopes, 45 and 47. They've also given us this horrible hybrid equation, which I hate, but will survive. So there's 2 different ways of doing this. I'll do method 1 up here. So same steps as normal. Work out the mass of the isotope that we have any information about. We have the time of flight of scandium-45, so we're going to work out the mass of the 45 isotope. Divide it by 1,000 and divide it by Avogadro's number. And your mass comes out as 7.4726. Times 10 to the minus 26 kilograms. So again, it's in the right range that we're looking for, that times 10 to the minus 26. So this is the mass of 45. It's worth labeling which isotope you're talking about at each time. So M for mass, 45, because we're looking at the 45 isotope. If you don't, it makes it a lot more confusing for the examiner to work out what you're doing. They're less likely to give you marks, especially error carried forward marks. So velocity of 45 squared equals 2 kinetic energies divided by the mass of 45. We don't do a subscript for kinetic energy because the kinetic energy is going to be the same for every isotope. That is how a mass spectrometer works. So they've given us the energy in the question. And you've already worked out the mass. And then V squared equals I want to square root that, so we get just V45, and the velocity of 45. This time it's been accelerated a bit faster than normal, so I've actually got quite a high kinetic energy. So I've kind of got in the range of 1 million now, but it's only 1 order of magnitude different to what you'd expect. So we've got the velocity of 45, and now we can work out the flight tube length, because it's going to be the velocity of 45 multiplied by the time of 45, which they've given us in the question. It's 8 times 10 to the power minus 7. It's even not taking very long to go there at all. And we end up with a length of the flight tube 1.31727 meters. I'm not rounding this down because we're going to use it again in further calculations. The length of the flight tube is the same for both isotopes. So now we want to work out the time it takes for 47. And we know that time of 47 is going to equal distance divided by the velocity of 47, which equals the 1.32 divided by V47, which we don't know. So to work out the velocity of 47, we need to do these top 2 steps again, but for isotope 47. So mass of 47 is going to equal 47 times 10 to the minus 3. we've got 7.8. 0.47. You can have a think, does that make sense? It's a little bit heavier than the mass of 45, so yes, that makes perfect sense. And then the velocity of 47, this time I'm just going to put it all in as 1, although I'd always advise against this. Kinetic energy is the same as before, because all isotopes are accelerated with the same kinetic energy, divided by the mass. And the velocity of 47 comes out as 8.18 times 10 to the minus 7 seconds. You think, does that make sense? Well, it's a little bit slower than the mass of 45. It's a heavier isotope, it should be slower. So the time of 47 equals 1.31727, the time divided by that 8.18 times 10 to the minus 7, and you come out with I'm sorry, ignore what I said there. Get rid of that. The velocity was actually 16.1116926. Oh no, this has all gone wrong. Anyway, so worked out velocity of 47 equals 16.1116926. So 69.26. We know the distance that it travelled was the 1.31727 meters. That's meters per second. So we worked out that in the first part of the question, which means the time of 47 equals distance over the velocity of 47. And again, if you're confused where that distance came from, just rewind the video a little bit and then it will show all the calculations back again. And that gives you the time of 1.18 times 10 to the minus 7 seconds. And then this is when you do the logical step. Does that make sense? Yes, because it's a little bit bigger than this one here. So massive calculation for 4 marks doesn't seem fair. That's because there is an easier way. And then this is going to be method 2. So we know that kinetic energy equals half the mass of 45 times the velocity of 45 squared. But that's also going to equal half times the mass of 47 times the velocity of 47 squared. And what we can do straight away is cancel out the 2 halves, because they're the same on both sides of the equation. We cancel them out. We also know that velocity equals distance over time. So we can say the mass of 45. This time we're going to substitute in distance over time instead of velocity. So distance squared over time of 45 squared is going to equal the mass of 47. And we're going to do the same with velocity here. So distance squared over the time of 47 squared. Now, distance is the same for both of them. That's why I haven't put a subscript on it, because they've got the same length of flight tube. So d squared will be the same for both of them as well. We can cancel them out. And with the mass of 45 and the mass of 47, if I converted it into kilograms, so divided by 1,000 divided by Avogadro's number, I'll do that to both sides of the equation. So those steps would also cancel out. So I can actually just now refer to the mass as just 45 and then just 47. I don't need to do all the weird converting into kilograms there. So the time of 45 they've given us, 8 times 10 to the minus 7, we can square that. And then this is going to be the time of 47 squared. So even though they've given us kinetic energy in the calculation, it's not actually needed. If we do it method 2, we don't need the kinetic energy, but they've given us kinetic energy. So if you're not as good at maths and you're not happy with this second method, you can use the first method and do it the normal way. And there's only ever been one example, and that was only in a specimen paper where they haven't given you that opportunity to do it both methods. So now we want to rearrange this. So I'm going to times both sides by the 8 times 10 to the minus 7 squared. So 47 times 8 times 10 to the minus 7 squared. I'll then times is going to equal 45, and I'm going to times both sides by time of 47 squared. And then I'm just going to divide both sides by 45 to get that. And then the time of 47 squared comes out as roughly that, I think. And then if you square root the answer, the time of 47 comes out as 8.18 times 10 to the minus 7 seconds, which is exactly the same as that one there. So both methods give you the same answer. Doesn't matter which one you use. The second method is quicker if you can get your head around all the cancelling out and the rearranging. Method 2 is probably the better one to use. But method 1 is most similar to all the other calculations you have to do on these ones. So actually, method 1 makes more sense logically with the other calculations. Method 2 kind of its own standalone thing.